Greetings, fellow geometers. Today, in Lesson 2.3, we shall discuss biconditionals and definitions. Whoosh. And this is a blank slide. Alright, here's a statement. If a polygon has three sides, then it's a triangle. Here's the converse of that statement. If a polygon is a triangle, then it has three sides. Let's look at this first one. If a polygon has three sides, then it's a triangle. Is that true? Yeah, that's true. How about if a polygon is a triangle, then it has three sides? Yeah, that's true also. Here's another way to state the converse. So another way to say if a polygon is a triangle, then it has three sides. You can say a polygon has three sides only if it is a triangle. And if both of those statements, the original statement and its converse, are true, we can kind of stick these two together into what we call a biconditional statement. And you can say a polygon has three sides if and only if it is a triangle. And when you do if and only if, it works in both directions. It means a polygon has three sides if it's a triangle, and a polygon has three sides only if it's a triangle. What it basically means is, it means that the statement and the converse are both true. So, does it matter which one you write first? A polygon has three sides if and only if it's a triangle? Or a polygon is a triangle if and only if it has three sides? It doesn't matter which way you write it because it works in both directions. The symbol we use is actually P if and only if Q. The arrow going in both directions. It means P implies Q, but Q also implies P. Right? The original statement is P implies Q. The converse is Q implies P. And if they're both true, then you can put them together like this. P if and only if Q. That means it goes both ways. It means P implies Q and Q implies P. And sometimes you'll see it as this little contraction. IFF means if and only if. So there's a little intro to biconditional statements. So, how do we write a biconditional? What is the converse of the following true conditional? So they tell us it's true. If the converse is also true, rewrite the statements as a biconditional. So this is true. If the sum of the measures of two angles is 180 degrees, then the two angles are supplementary. So what's the converse of that? The converse would be if two angles are supplementary, then the sum of the measures of those two angles is 180 degrees. And is that true? If two angles are supplementary, then the sum of their measures, yeah, that's the definition. Wink, wink. So the converse is true, so you can make a biconditional statement by joining them together with if and only if. So you can say the sum of the measures of two angles is 180 degrees if and only if the two angles are supplementary. Or you can write it the other way. Two angles are supplementary if and only if the sum of the measures of the two angles is 180 degrees. Alright, so try this one. Pause and push play when you're ready to see the answer. So what is the converse of the following true conditional? If the converse is also true, then you can rewrite it as a biconditional. If two angles have the same measure, then the angles are congruent. Okay, so that's our original statement. If P, then Q. So let's write the converse. R, who's R? So the converse would be if two angles are congruent, then they have equal measure. Is that true? Yeah, that's true. That's the definition of congruent angles. So, our statement is true, and our converse is true. that means that we can write the biconditional, P if and only if Q. I can write the definition now, and it doesn't matter which one I put forth first. Two angles are congruent, or if two angles have equal measure. So the biconditional is two angles are congruent if and only if they have equal measures. So a biconditional combines the original statement and its converse as P if and only if Q. So example, a point is a midpoint if and only if it divides a segment into two congruent segments. P if and only if Q. Alright, so what are the two conditional statements that form this biconditional? A ray is an angle bisector if and only if it divides an angle into two congruent angles. So let P and Q represent, let P be a ray as an angle bisector, and let Q represent a ray divides an angle into two congruent angles. So what are the two conditionals? P implies Q would be, if a ray is an angle bisector, then it divides an angle into two congruent angles. Q implies P would be, if a ray divides an angle into two congruent angles, then it's an angle bisector. So here's the biconditional. See if you can figure out the two conditionals that form it. Alright, so this right here is P if and only if Q. So we can let P be two numbers are reciprocals, and we can let Q be their product is 1. So one of the conditionals would be P implies Q. If two numbers are reciprocals, then their product is 1. And Q implies P would say, if two numbers have a product of 1, then they are reciprocals. And throwing a fit is the secret code phrase for this lesson. Throwing a fit. Okay. So, writing a definition as a biconditional. Is this definition of quadrilateral reversible? If it is, write it as a true biconditional. Definition. A quadrilateral is a polygon with 4 sides. So let's think of this as a conditional. If a figure is a quadrilateral, then it is a polygon with 4 sides. So we had to get our hypothesis and our conclusion. Now write the converse. So now Q implies P. If a figure is a polygon with 4 sides, then it is a quadrilateral. Since the conditional and its converse are both true, it is reversible. So we can write it as a biconditional. A figure is a quadrilateral if and only if it is a polygon with 4 sides. So, number 3. Is this definition of straight angle reversible? If yes, write it as a true biconditional. A straight angle is an angle that measures 180 degrees. Alright, so what would our conditional look like? So our P implies Q would be, if an angle is a straight angle, then it measures 180 degrees. Our converse would be, if an angle measures 180 degrees, then it is a straight angle. So are both of those true? If an angle is a straight angle, then it measures 180 degrees. Yep, that's true. If an angle measures 180 degrees, then it's a straight angle. Yes, that is also true. So the biconditional, P if and only if Q, would be, an angle is a straight angle if and only if it measures 180 degrees. So one way to show that a statement is not a good definition is to find a counterexample. So, which of the following is a good definition? A fish is an animal that swims. Well, let's see. Humans are animals and they swim. Dolphins are mammals. They're not fish. They swim. There's a lot of animals that aren't fish that swim. So choice A is not reversible. You can't say if an animal swims, then it's a fish. Right? A whale is an animal that swims, but it's a mammal, not a fish. What about B? Rectangles have 4 corners. Well, what's a corner? Right, here's something that has 4 corners. Is that a rectangle? What's your definition of a corner? You got to be real specific. So for B, corners is not clearly defined. All quadrilaterals have 4 corners. So C, giraffes are animals with very long necks. Is that reversible? Is any animal with a very long neck a giraffe? That's very long is also not precise. It's not reversible either. Ostriches have long necks. Just because an ostrich has a long neck doesn't mean it's a giraffe. How about D? A penny is a coin worth 1 cent. Is that reversible? A coin worth 1 cent is a penny? Yeah, it's a good definition. It's reversible. All the terms are clearly defined and precise. So, look at this one. Is the following statement a good definition? Explain your thoughts. A square is a figure with 4 right angles. Is that a good definition? It might sound like a good definition, but is it reversible? Is a figure with 4 right angles definitely a square? No, because a rectangle has 4 right angles, but it's not a square. So just saying 4 right angles is not enough. That's the end. Goodbye.